Welcome back, everybody. This is our video solution to problem 1 from Quiz 11, Spring 2023, Math 302 at Cal State Fullerton. And in this problem, we are given two commutative rings, R and S, not necessarily with a multiplicative identity. All right, it's going to turn out the commutativity is not super important, or I should say important at all to this. It's just we've been defining ideals in terms of commutative rings in class. So I'm keeping the commutative rings in here for this problem, but if we drop this commutativity and we define ideals for non-commutative rings, then everything we're saying here will be true with appropriate modifications. So we have a function f between these two rings, R and S, and we're going to call it a ring homomorphism if for all x, y, and r we have that f of the sum, x plus y, is the sum of the f's. So f of x plus y is f of x plus f of y. And also that f of a product is the product of the f's. So f of xy is equal to f of x times f of y. This second one, the product version, that should remind you of the norm map, this multiplicativity condition. All right. The first one should not remind you of the norm map. Right? This additive condition is not actually true for the norm map in general. Okay, fine. But we're going to assume that we have a function that satisfies both of these at once. And now we want to show that a certain set, so we're calling this k of f, and this k is, this is a secret k letter. K stands for the kernel. All right. If you've taken linear algebra, you might know this as the null space. So the kernel of a ring homomorphism is all of the elements in the domain whose image under this map F is 0, right? So the F image is 0. And we want to prove that this set is an ideal of the domain R. All right, so in class we gave a condition for a subset to be an ideal. In fact, it was 3 things that we had to check. So the first thing that we have to check is that 0 is in the kernel. All right, so that's the first thing. Well, that would mean we would have to show that the F image of 0 is 0. Note, by the way, right, when we talk about this 0, this is the 0 in the ring R, whereas this 0 here, right, because it's an F image, right, this is the 0 in S. Okay, just to keep that straight. So we need to show that f of 0 is equal to 0. Okay, fine. How can we do that? Well, let's use this additivity condition. F of 0, of course, that's equal to f of 0 plus 0. And now by this additivity condition, I know this is f of 0 plus f of 0. So now I have elements f of 0 and then f of 0 plus f of 0, and they're equal, and these are all elements in S. I can add the additive inverse of f of 0 to each side. So I'm going to add negative f of 0. And if I do that, well, on the left-hand side, I'll get f of 0 plus negative f of 0, which will be 0. And on the right-hand side, I'll get f of 0 plus f of 0 plus negative f of 0, and that will cancel this last f of 0, and I'll just get f of 0. Hey, there we go. We were able to show that the image of 0 is 0. All right, so that's the first thing we have to check. How about the second thing? We need to show that this set k of f is closed under addition. All right, so we need to show that if x and y are in k of f, then x plus y is in k of f. Okay, fine. So we assume x and y are in k of f. What does that mean? So x, y in k of f, that means that their f images are 0. So f of x is 0 and f of y is 0. Okay, but I need to compute f of x plus y. But we know that f is a ring homomorphism, so f of x plus y is f of x plus f of y, and we just established that those are both 0. Therefore, x plus y has f image 0, and so it is in the kernel. Okay, finally, the third piece. We need to show that the kernel absorbs R multiplication. So if X is in the kernel and little r is in R, then Rx is in the kernel. Okay, well, let's give that a try. So we know that, again, X is in the kernel, which implies that f of x is equal to 0. But we want to show that f of Rx is equal to 0. Well, what is f of Rx? Well, we know that f is multiplicative. We haven't used that yet, right? Just like the norm map. And so f of Rx is equal to f of r times f of x. And f of x is equal to 0. And one of our early properties of rings was that if you multiply any ring element by 0, you must get the 0 element. And so this implies that Rx has f image 0, and so Rx is in the kernel. And the combination of all three of these things implies that K of f is an ideal of the ring R. Okay, there we go. And that's how we show that a subset is an ideal. We'll see you next time, everybody.